Given a set of paired data, regression techniques allow the analyst to view different types of models to decide which model best represents the relationship between the two variables. One example might be the relationship between SAT scores and freshman grade point average by taking a sample of students who've completed their freshman year of college. We can look at X, their SAT scores when they were seniors in high school, and Y, the values of their GPA the freshman year. Look at a graph of the scatter plot of the points representing each student's SAT and GPA, and then look to see what type of function best displays the relationship between SAT score and freshman GPA. We have various ways of writing linear equations, and linear equations are the most commonly used type of models. They're simple to understand, and many things in the real world are linear. The thing we need to watch out for is that we will have three possible ways of writing a linear equation. In algebra, we use y equals mx plus b. Many statistics books use y equals a plus bx, where b now is the slope and a is the y-intercept. And some statistics books use y equals b0 plus b1x. This is used in anticipation of multivariate statistics, when instead of using 1x to predict a y, for example, using SAT to predict freshman GPA, we use two or more variables, for example, SAT, high school GPA, and an index based on the number of activities the student participated in high school to predict their freshman GPA. And then we'd have something like y equals b0 plus b1x1 plus b2x2 plus b3x3. But no matter how you slice it, the linear equation has three terms: y equals, and then some number in front of the x, that number being the slope, and then the y-intercept. We're going to use y equals a plus bx, because that's a typical statistician's way of writing a linear equation for two variables. Now, the regression equation, of course, is an approximation. It is a model, because in the real world, most things do not line up. And what we are trying to do is get information from a sample set of data to help us make approximations of what information we would have if we could get the information on everybody in the population. In analyzing data comparing the fat content of pizza and the caloric content of those slices of pizza in a previous lecture, we drew a line using 2 points on the graph. Now we are going to use the power of the regression model. That is, computers and many calculators have built into them software that allows you to tell the calculator or computer what type of model you want, and then it will both construct the model, in this case a line for a linear equation, and give you the numbers associated with that equation. So we are going to look at the pizza data once again. But this time we're going to allow the graphing calculator to give us a linear equation and see how well it matches up with the data. Here is a scatter plot of our pizza data. The x-axis is fat in grams. The y-axis is the caloric content of each of the various types of pizza. Now, by going to the calculator's regression menu, we can get a regression equation. And here is that equation. Of course, because the calculator allows the numbers to wrap around, it may be a little hard to read. But basically, what it says is that the equation is 253 with a small decimal fraction plus 6.479, etc., x. That says that the y-intercept is 253. If the pizza had no fat, there would still be 253 calories. And the slope is 6.48 approximately. That says if we add another gram of fat, we would add approximately 6.48 calories to that pizza's content. Let's take a look at the graph. Here you can see the line coming out. This is the regression line. And you'll notice that the y-intercept over here is at approximately 250, as we said it would be. That y-axis, of course, is scale. That is not the origin. And you'll notice that only a few points of the data are actually touched by the line. But the line does a very good job at approximating the relationship between fat content and calories in pizza. Thus, we have an effective linear model, and we've obtained that by using the regression menu in the graphing calculator, the TI-83. Not all regression models are linear. We should recall that calculus was created because many real-world situations did not have a constant rate of change. In our discussion of algebra, we looked at the quadratic function, and we actually looked at quadratic models. Let us go back to one of those quadratic situations and see how the graphing calculator uses its regression menu to give us a quadratic equation to model a set of data. The data I refer to is the population density of the United States every 10 years from 1790 through 1990. Let's go to the graphing calculator and look at the data. And here is a scatter plot of that data. The x-axis is the census year. The y-axis is the population density of the United States. I'd like to recall, for those of you who may have forgotten, that the typical trend is upward, and it certainly doesn't look linear. But there are three occasions, three periods, in which the population density of the United States decreased. The first is right here, 1800 to 1810. That was, of course, due to the Louisiana Purchase, adding a vast amount of territory to the area of the United States with a very small addition of population during those 10 years. The second reduction in the population density of our country is right here, 1840 to 1850. This was due to the combination of the results of the Mexican-American War, where we obtained numerous future states, such as California and Colorado, as well as the entry of Texas into the United States. Texas was a republic, and in 1845 became a state. And thus we added vast amounts of territory, Texas, Colorado, Utah, California, New Mexico, Arizona, and added a very small amount of population. The final location or year period where the population density decreased only slightly, though, is right here, 1950 to 1960. And of course, that was due to the addition of Alaska as a state. Alaska has a tremendous amount of square miles and very few, exceptionally few, people in terms of increase to our population. And here are the data. Again, this is an opportunity to take a look and recognize that what we see apparently can be modeled by the right side of a parabola, an up parabola, so therefore we need to use a quadratic regression model from our calculator. And we can do that, and when we do that, the calculator gives us this equation. And you'll notice the equation, it's kind of hard to read, but that's okay. That's what happens when you have a calculator with a limited number of characters per line. But the fact is, what we have is an equation in ax squared plus bx plus c form. Previously, when we looked at this particular set of data, we used the quadratic form y equals a parentheses x minus h squared plus k. Now, the coefficient of the x squared term is 0.001568, etc. That is the a term. Very, very small, because we have a slow growth in terms of every 10 years. The plus the negative 5.59, etc., x, that is the what's called the linear term. That's the bx. So that is about approximately negative 5.6 if we were approximating with a round off. And our c term, our y-intercept, is 4,985.054, etc. By the way, looking at that y-intercept, it really has little meaning in this particular set of data, because that would be the population density of the United States in the year zero. Remembering that 1790 was the vertex, and therefore this would be the other side of the parabola, which in fact would indicate that the United States had had great population density 2,000 years before its creation. Obviously that's silly, but we simply use the equation for years from 1790 to the present. Now, let's take a look at the graph with that quadratic model. And you'll notice, again, the model doesn't line up perfectly because the real world is not perfect. But it is a very close approximation to the data. And we can use that equation to investigate the relationship between years and the population density growth of the United States, as well as to make forecasts into the near future. It is a quadratic model, and it makes sense to use it. We could see that because we've visualized the model and compared it to the fit against the data. In our excursion in algebra, we also discussed exponential functions. And perhaps we should now look at a set of data that would help us use the exponential regression menu in our graphing calculator to come up with a model that would represent the relationship between x and y in something we believe to be exponential. And the model we're going to use is the federal expenditures on Social Security, Medicare, and Medicaid over time from 1960 through 1980. And we are going to look at the data and then realize that it could be modeled by an exponential, allow the graphing calculator to come up with an equation, and then evaluate the model in terms of the original data points. Here are the data. The x-axis is the year. The y-axis is the cost in millions of dollars for the expenditures by the federal government in that year for Medicare, Medicaid, and Social Security. This is 1960, 1965, 1970, 1975, and finally 1980. Looking at the data, this is a candidate for exponential regression. It appears that as we go from 1960 to 1980, in each 5-year interval, the increase of costs is increasing at an increasing rate, an exponential rate. Let's take a look at the equation given to us by the regression menu in the TI-83. And here is that equation. It is y equals 4.06 and a bunch of stuff times, and again this snowflake represents times 1.4, 1.143, etc., raised to the x power. So we have our a times our b, the base, raised to the x power. This is an exponential function. And remember from our lecture on algebra that we said that for an exponential function, the base, b minus 1, gives you the rate of increase if the b is greater than 1, which it is, for the model. And since 1.14 minus 1 is 0.14, this says during the period 1960 through 1980, we're dealing with an exponential function increasing at approximately 14%, or if you'd like, 14.35%. So let's take a look at the graph. And here is the graph of this exponential function. You'll notice it comes exceptionally close to each of the 5 points. And the graph itself starts and increases more and more rapidly, and if allowed to continue, will rise exponentially into the future. Obviously, since 1980, the government has taken steps to modify this model, and hopefully they will continue to take steps so we will prevent extreme exponential growth of these expenditures so that my grandchildren will have an opportunity to have the kind of retirement that hopefully all of us look forward to. Meanwhile, we know that this function was correct and based on fit. Sometimes we have a situation where one function will not make a good fit, and in fact we need to use something called a piecewise determined function. And that is, for different parts of the data, we use a different function. A great example of this has to do with the number of colleges that belong to the NCAA in recent years. When we look at the data, we'll see that there's an obvious change in the relationship between the year and the number of colleges. And this would best be represented by two separate models. Let's take a look at those data. And here are those data. The x-axis represents individual academic years, starting with 1981 and progressing through 1995. The y-axis represents the number of colleges which belonged to the NCAA. You'll notice until the key year of 1989, the growth was rather slow. A line with a very small slope could represent these data. After 1989, it appears that a line with a much steeper slope would be used to represent the data. We have a candidate for a piecewise defined function. We could obviously, if we wanted to take the time, use the graphing calculator to create those two different linear models. And when we do, by the way, the slope of the first half of the data turns out to be around 2 or 3, while the slope of the second half of the data is approximately 30. And now, from looking at those data and considering a piecewise defined model, a very interesting question can be asked. And that question is, what was so special about 1989? I'm not very sure of the answer, but my interest in sports leads me to believe that the growth of cabled stations that showed professional, I should say college football and basketball games in the late 80s and early 90s caused many colleges which were not members of the NCAA to join to share in the revenue rewards, because obviously when any NCAA team plays on TV, that team gets paid. If it's a conference member, the conference schools get paid, but all NCAA members gain some money from this. And obviously with the tremendous growth, one might say the exponential growth, of football and basketball games on television, those games that have NCAA teams playing would reap rewards for members of the NCAA. And therefore, in 1989, the slope of the model changed drastically. Very interesting for those of us who are concerned about the influence of the NCAA on colleges and the influence of sports on colleges. But now let's turn to another model that we looked at in our algebra sequences, and that is the cubic model. In that particular lecture, we talked about the growth in American soccer players. You may recall that we said that the growth was increasing at a decreasing rate, and then all of a sudden, in the late 1980s, the growth of American high school soccer players increased at an increasing rate. And we had something called an inflection point. And with that point, we saw that Title IX caused high schools to add girls soccer teams to their total of teams, and therefore the number of soccer players began increasing at an increasing rate. Let's take a look at another example of a set of data that could be modeled by a cubic equation. And this is data on American life expectancy. Let's go back to the graphing calculator. And here is the life expectancy data. For every year, actually every 10 years, this is the life expectancy of an American citizen born that year. My understanding is this is the age at which the median person born that year would die. You'll notice the life expectancy has been increasing throughout the 20th century. You also may say it looks like a candidate for a piecewise defined function, and that may be true. But you will further notice that in the early years, the growth in life expectancy seemed to be increasing at a somewhat increasing rate, while in the latter part of the century, the growth was probably increasing at a bit of a decreasing rate. Let's take a look at the model and see if it makes any sense. Here is the equation, and again, now we have quite a lot of numbers floating around, but indeed it's quite easy to understand because this is a cubic model, which is the form ax cubed plus bx squared plus cx plus d. So here is your a, but notice it's negative 2.1 times e to the negative 5 x to the third. So it's a very, very small coefficient for the x to the third term. Then we have our quadratic term. That is the term that's in front of the x to the second. And that is 8.35 with a bunch of numbers after it, but multiplied by e to the negative 4. Again, that is scientific notation for 10 to the negative 4, another very, very small number. Our linear term, in which a number is multiplied by x, here it is. And of course, that number is approximately 0.411. And finally, our last term, our d, which would be our y-intercept, and that is 46.6. Again, the meaning of these particular terms is not as important as the usefulness of this equation as a model. So let us go and take a look at the graph of this equation versus our data points. And you'll notice that the model follows the data points quite carefully, and certainly we could use this model to represent life expectancy for Americans in the 20th century. There is one danger that one should recognize. Look at the very right side of the graph. It appears that that function is leveling off. If we were to graph it any further, because it's a cubic, we would see that the graph would start a downward trend, which would be saying in the 21st century, life expectancy would be decreased for the average American. This is probably not correct, but again, we are best to use this model for the time period for which we have data. And for that time period, the cubic is a very effective model, and we could ask, where is the inflection point and what happened at that inflection point to cause the increase in American life expectancy to go from increasing to a decreasing rate? Some sets of data do not require a particular model. Simply looking at the graph of the data allows us to make predictions and make analyses of what the relationship is. Such a set of data was published by the American Mathematical Society about the number of mathematics PhDs issued each year during the latter part of the 20th century. It also showed data on the percentage of those PhDs in mathematics that were American citizens. Let's go back to the graphing calculator and look at those data sets and see that we really do not need a model to understand what is going on. Here are those data. You'll notice in the early part of this graph, in the 1970s, the number of PhDs in mathematics was decreasing. But then there was a turning point, and they appear to be increasing. And although this might be something like a parabola and might be a quadratic model, what really is important is something was going on. And what's going on probably was the need for math PhDs in areas of financial analysis and in terms of computer systems design and all the work being done with software development. So we see a decrease followed by an increase, a fairly steep increase in the number of PhDs. Would you like to take a guess of what the data revealed about the percentage of American citizens who were receiving these degrees? What the graph reveals is that in the mid-1970s, there was approximately 75% of the math PhDs issued in this country were issued to American citizens. By the mid-1990s, that was down to 45%. We don't need a mathematical model to tell us that something is going on. Foreign citizens are coming to this country in ever-increasing numbers and getting more and more mathematics PhDs. What is going on? That is an educational problem that's beyond the scope of this lecture series. Once we have found a model, at least a function we believe is a good model for our data set, we need to validate that model. And there are two important things to look at in the validation process. The first we actually have already looked at, and that is the fit. When we drew a straight line or a cubic or a quadratic parabola, we examined how close that particular graph came to the actual points. Did that graph closely follow the points? Was there a good fit? If there was, then that function is an excellent candidate for a model. The second thing is to use an algebraic process called the residual. the difference between the actual y value at a point and the predicted y value for that x value on the curve or line that represents the model. And that difference, which could be positive or negative, is squared to get rid of negatives, and the sum of those errors or the sum of those residuals are examined. Here is a picture of a linear model with some points, and one of those points has been selected, and we notice that the residual is the actual value of y, the value of y for that point, minus the value of y on the line for that particular x. It is a positive residual. For those points below the line, the residual would be negative. And again, we square all the residuals because we want to get rid of the negatives. We sum the squares and we get the sum of squared error. The best fit model will minimize the sum of squared error. The earliest work on minimizing the sum of squared error was done by Adrien Legendre, another French mathematician who lived and worked in the early part of the 19th century. Residual analysis can further be done by looking for a pattern among the residuals. Are all the residuals for the lower values of x's small and the residuals for the larger values of x's large? Or do you see a pattern, for example, a line or a parabola in the residuals? The residual graph should appear to be random. All of this is used to analyze the data. Some people would use the correlation coefficient as a measure of the validity of a model. This is sometimes appropriate and sometimes is not. The correlation is an index of the relationship and how strong it is between the x and the y variable. The numerical value can vary from -1 through +1. The correlation coefficient can be influenced by a small subset of data, or even by 1 point. Data with a correlation coefficient close to -1 or +1 may not be as strongly related as indicated by the correlation value. Correlation should be examined, but it must be used only after first looking at the fit and the residual analysis. Those are much better tools for assessing the validity of a model than the correlation coefficient. It is very common for the correlation coefficient to be confused with causation. Two variables that have a high degree of correlation may not have a causal relationship. A good example is that there's a strong positive correlation between the number of Methodist ministers in New England and the amount of rum imported through Boston Harbor during the 19th and 20th centuries. The correlation is due to population growth, increasing the number of Methodists in New England and increasing the demand for rum. It has nothing to do with Methodist ministers drinking more alcoholic beverages. There is a strong positive correlation between shoe size and the size of a student's vocabulary among elementary school students. Does that mean that a parent should stretch his or her child's feet to increase their vocabulary? That would be nonsensical. The correlation is due to the fact that older children in an elementary school have bigger feet and have larger vocabularies than the children who are smaller and in lower grades. It makes a lot of sense not to use correlation in that case as causation. Another good example is that there's a strong correlation, and it's negative, between the population of the state of Louisiana and the land area of that state. Does that mean that as we increase the population, the land falls off because the people are stomping their feet or something and causing the land to fall away? No, that is simply a spurious relationship that has nothing to do with anything else and is silly to consider. The square of the correlation coefficient, that is, the correlation coefficient squared, which gets rid of the negative and is a fraction between 0 and 1, is called the coefficient of determination. And it represents, as a decimal, the fraction of the change in the response variable, y, that can be explained by its relationship with the x variable, which, of course, is the explanatory variable. The explanatory variable attempts to explain, in our model, the y variable, which is the response. Now, hopefully we've had a small look, a quick look at correlation, at regression analysis, at using algebraic functions to model real sets of data, and using the regression menu of a graphing calculator or possibly a computer to obtain such a model. In our next statistical lecture, we will talk about the central limit theorem and hypothesis testing.